We're jumping into graphing rational functions. And so rational functions are in the form. In the form of, let's say, y is equal to some f of x over g of x. Where f of x and g of x are polynomials. And we have to say that g of x cannot equal 0. So when we're looking for the domain of a rational function, we have to exclude all values which set our denominator equal to 0. So to find the domain, of a rational function, it is all real numbers except the values of x that set the denominator equal 0. And so rational functions can have asymptotes, and there's what are called vertical asymptotes and horizontal asymptotes. So asymptotes. And there's also what is called oblique asymptotes, but let's first talk about horizontal and vertical. So a horizontal asymptote what's happening is, oops, I don't know why that happened. As your value of x goes to positive infinity or your value of x goes to negative infinity, your y value is just going towards one number. And so the limit as x goes to plus or minus, could be both, infinity of your function. Let's just say f of x over g of x. Is equal to some value, let's call it L, where L is equal to a constant. Okay, so pictorially what's going on here. So let's say we have our x and our y axis, and as x is going to positive infinity, it's going to start hugging some value of y. So it's going to get closer and closer to this y value. Might never touch it. It might cross it, and if it crosses it, then it's going to hug it on the other side. So you might have something where, who knows, it could come down like this, and then as x is going to negative infinity, it's hugging another value. So let's call this maybe n. So notice here, as the limit as x is going to negative infinity, our y value we're getting closer and closer to is n. Our case there. So it's going to get closer and closer to that value. Okay, so those are what horizontal asymptotes are going to do. As it goes off to infinity or negative infinity, your graph is going to get closer and closer to one particular y value. We'll talk about in a minute how to find those. And then vertical asymptotes. So these are going to occur as you're heading towards some x value. Your y value is going to shoot off to some positive or negative infinity. So as x approaches some value, let's just call it c, of our rational function, f of x over g of x, then this is going to equal plus or minus infinity. So maybe this is where c is on the x-axis. Let's draw a vertical line here. So different things could be happening as we're approaching it on the left-hand side. Could be shooting off to positive infinity. Or maybe as we're approaching it on the right-hand side, it's shooting down to negative infinity. So we've got a vertical asymptote at C. And actually the graph I just drew actually has a horizontal asymptote. As x is going to negative infinity, our y value is getting closer and closer to the x-axis. So y equals 0. And as x is going to positive infinity, this is going to a y value of 0. But the vertical asymptotes, as you get closer and closer to the x value, it shoots up or down to positive or negative infinity. One thing you have to notice here is graphs can never cross a vertical asymptote. So it can cross a horizontal, and it will be able to cross an oblique. We'll talk about obliques later, but it can never cross a vertical asymptote. And the reason why that is are how you find your vertical asymptotes. So vertical asymptotes, these values occur when our denominator is equal to 0. And so we know it's undefined when our denominator is equal to 0. It's not in our domain. So vertical asymptotes occur at values that set the denominator equal to 0. But not also the numerator. Okay. If it sets both numerator and denominator equal to 0, what's happening is that it's a hole there. It's still undefined, but it's a hole. Let me just turn this off. So values that set both equal to 0. Is a hole in the graph. At that value. Okay, so let's maybe look at a couple examples before I go any further. So find the domain of each rational function. So let's say you had r of x. This is equal to x all over x to the fourth minus 1. Okay, so domain, again, are all real numbers that we can plug into a function and get back a real number. And so the only problem we're going to have is when we have values which set this denominator equal to 0. And so we need to exclude values which make x to the fourth minus 1 equal to 0. Okay, so I need to factor this, or I need to solve for this somehow. Two terms, try difference of squares, difference of cubes, but this looks like a difference of squares to me, because this could technically be rewritten as x squared quantity squared minus 1 equals 0. So difference of squares here. So I have x squared minus 1, x squared plus 1 equals 0. Difference of squares again, x minus 1, x plus 1. But a sum of squares is not factorable with a real number, so I'm just going to leave it like that. And so setting each piece equal to 0, x minus 1 equals 0 when x is 1. X plus 1 is 0 when x is negative 1. X squared plus 1 equals 0. X squared equals negative 1. Take the square root of both sides. But a square root of a negative we saw was negative 1 was I, so plus or minus I. Okay, so we have to exclude those values from our domain. So technically, right, if we put this on a number line, we would have an open circle at negative 1, we would have an open circle at 1, and we could have any x values to the left of this, any value in between it, or any value bigger than 1. So interval notation, I could write it as negative infinity all the way to negative 1, not including, so I'll put a parentheses. Union, I'm hitting everything between negative 1 and 1. So put parentheses around those, union everything from 1 to infinity. So if I was to look at this, x equals 1 and x equals negative 1, notice they don't set the denominator or numerator also equal to 0. These don't set the denominator equal 0, or sorry, they do set our denominator, but they don't set the numerator equal to 0. So these are where vertical asymptotes occur. have, and normally you don't see these on the graph, but we put them on our graph to represent that they're occurring here, these dotted lines. In this case, because it's a vertical asymptote, vertical lines. So somehow in here, these graphs, I don't know which direction, but I could figure it out, are hugging these lines. Could maybe be a parabola shape in between. Could look like a cubic in between, but somehow they're hugging these lines on each side. And soon we'll get those tools that we can figure out what's happening. Let's see. Use the graph shown to find the domain and range of each function, the intercepts, if any, horizontal asymptote, if any, a vertical asymptote, if any, and an oblique asymptote, but I won't show you that yet. Okay, so you're given a graph. Let's see, a horizontal. Okay, so again, find the domain, oops. Let me change that picture then. I'm going to make it so it's not crossing the horizontal. Okay, so the domain and range. So from here, you should be able to tell what the domain is and what the range is. So what are all the X values you would hit on that graph? Or what is the X value you don't hit on that graph? So right here we have a vertical asymptote.
You don't hit 2?
Right. So we don't hit 2. So on our graph, that X cannot be 2. And so it's going to be all real numbers but 2. So there's so many ways that we can write that. So negative infinity all the way to 2, parentheses, union, parentheses, 2 to infinity. So it's, and then the range, right? That's all the Y values you hit. So notice this graph, right? Because this is shooting downwards. I'm hitting always the negative infinity, coming up, coming up, coming up, coming up, coming up. All these Y values, right? But I have this Y value at 4, where my graph is getting closer and closer to, it's hugging it. I said it could cross it, but I made it so it doesn't. And then we're hitting all the Y values from 4 to infinity. Because of this piece right here, right? So it's going up forever, so you're hitting all the Y values going up. And so our range is going to be all values except Y can't be 4. So from negative infinity all the way up to 4, parentheses, union 4 to infinity. a horizontal asymptote, you can see that there is one. These are lines. So when you give an asymptote, it's stated as a line. And so horizontal lines are in the form of y equals. So it's y equals 4. Our vertical asymptote, so vertical lines are always in the form of x equals, and though this is x equals 2. And wanted to know about any intercepts. Well, this one right here, x and y intercepts are the same. It's crossing at the origin. And then oblique, no. Okay, so horizontal asymptotes, they have to do with the degree of the numerator and the degree of the denominator. So there's 3 different possibilities that could occur. So find the degree of the numerator. And the degree of the denominator. Okay, so let's just say, so I don't have to write it out each time, the degree of numerator, degree of denominator. Let's just say that when we looked at it, we found that the degree of the numerator was m. And we found that the degree of the denominator, let's say, was n. So there's 3 different possibilities that can occur. If the degree of the numerator, wow, why shouldn't I just said I wasn't going to write this down. Let me just write it out once. A numerator is larger than the degree of the denominator. Okay, so that would mean that my value m, mathematically, I can write m is greater than n. If that's the case, there's no vertical asymptote. I'm sorry, not vertical. We're talking about horizontal. No horizontal asymptote. There is an oblique asymptote at the quotient of the numerator divided by the denominator. Okay, I didn't even talk about oblique. Basically what's happening is you might have a line where your graph is getting closer and closer to that line as it goes off to infinity. My you know, kind of, I have no idea. You might have a vertical asymptote here. And it might look like something like this. So this would happen if the numerator was only one larger, because it would give us a quotient would be linear. But it's possible that the numerator is 2 larger, 3 larger. So depending on that, depends on what type of shape it's going to hug. So you might have something where the oblique was a parabola. And so what's happening is it's going to be somehow hugging this shape, and I don't know what it looks like, as it goes off to infinity. Okay, but we'll talk about those more later. Right now, I don't want to concentrate on the oblique. I want us to get better at the other ones. But that's what's going on with oblique, or what oblique is. So if the degrees are the same, so we got 1 degree of the numerator is larger. Okay. 2, the degrees are the same. So if m is equal to n, then you have a horizontal asymptote. Is at y equals, let's say, a divided by b. A is the leading coefficient of the numerator. And b is the leading coefficient of the denominator. So that was a number in front of the variable raised to the highest power. And then last case scenario is where the degree of the numerator is a smaller number, is less than the degree of the denominator. If that's the case, we also have a horizontal asymptote. And it's at your x-axis. So horizontal asymptote is at y equals 0. Your x-axis. If you think about it with the logic, if your denominator is growing much, much faster than your numerator, think about it. If you have 1 over 10, right, that is 1/10. If we have 1 over 100, that is 1/100. If I have 1 over 1,000, 1,000ths. And so as this number down here is getting huge, right, what's happening to our value? So 1 over 10,000ths, or is 10,000ths. So as this goes to ... 1 over infinity, this is going to go to 0. So that's if the degree in the numerator is smaller. If the degrees are the same, it's basically growing at the same rate. And so basically they kind of divide each other out, leaving us with a numerator, leading coefficient of the numerator over the denominator. Where if the numerator has a higher degree, you're getting numbers that are blowing up here. So maybe 100 over 1, 1,000 over 1, 10,000 over 1, 1,000,000 over 1. No, that's blowing up, going to infinity. I mean, these could be growing at a slower rate, but if these are growing faster, it's going off to infinity. So find the vertical and horizontal asymptote, if any, for each rational function. So if you have r of x is equal to 3x plus 5 all over x minus 6. Okay, so vertical asymptotes. This is values which set the denominator equals 0, but not also the numerator. Well, I can see that they're not being set equal at the same value. So x minus 6 is equal to 0 when x is equal to 6. If I plug in 6 into the numerator, that is not going to give me 0. And so x equals 6, this is our vertical asymptote. Here we need to look at the degree of the numerator. And we need to look at the degree of the denominator. So degree is the exponent of the variable to the highest power. It's not shown, so it is 1 for both. So if they're the same, we have to look at the leading coefficient of the top over the leading coefficient of the bottom. So our leading coefficient, LC, I'm going to call LC, is equal to, for our numerator, is 3. And for our denominator, our LC, number in front of x is 1. So we have a horizontal asymptote at y equals leading coefficient of the numerator 3 divided by leading coefficient of the denominator of 1. So y equals 3.
So if the degree of the numerator had been 2 and the degree of the denominator had been 1, it would be 2 over 1 instead of 3 over 1 right now?
Oh, if the degrees were different?
Yeah, first.
The degrees are, if the degrees were different, then it's, and if this was a 2 here, are you saying?
Yeah, there was a 2 there and the bottom was the same.
If
then it would be 2, then y would be 2 over 1 instead of 3 over 1?
No, because if this was a smaller degree here, and then the top, then it doesn't have 1. These would have to be the exact same power, and you would just then look at the leading coefficient of the top over the bottom in order for that to occur. Let me just rewrite it, 3x. plus 5. I don't even remember what it was, x minus 6. So if it had been like, say, h of x is equal to x cubed minus 8 all over x squared minus 5x plus 6. So the degree of the top in here is equal to 3. The degree of the bottom is equal to 2. So since 3, the degree of the numerator is bigger, then there's no asymptote or no horizontal. Because this grows much faster than this does. And so bigger number on top divided by a smaller number is going to blow up.
Okay.
Where then vertical asymptote, I have to factor. So it's really helpful that you factor both the numerator denominator. I see this as a difference of cubes. I'm going to just factor it really quick just because I see that we're running out of time. This could be x quantity cubed minus 2 quantity cubed. So difference of cubes factors that will factor as x minus 2 all times x squared, let me think, plus 2x plus 4. All over, so factor our denominator. Two numbers that multiply to 6 but add to -5 are -2. So x minus 2, x minus 3. So vertical asymptote, notice x equals 2. Set both the numerator and denominator equals 0. So it's not part of our domain, but it's not a vertical asymptote because of that. So x equals 2 is not a vertical asymptote. It's going to end up being a hole in the graph. At x equals 2, and we could figure out that y value by canceling those factors out and then plugging into wherever we saw an x. So maybe I should say x equals 2. The value though here, x equals -3, this just sets the denominator equals 0. So this is a vertical asymptote. X squared plus 2x plus 4 doesn't factor over the real numbers, or let me see, -p. Yeah, it's an imaginary number if we use the quadratic formula. I always know that this cubic or this trinomial, when I'm factoring a cubic, isn't factorable. I wanted to rush through one more example. So your question, Timothy, helped me do that. So we'll pick up on this on Thursday, but we're just getting into where we can start putting all these pieces together and start graphing this. And so this is, like I said, 5.3 and 5.4 in our textbook kind of intertwined. So let me stop the video, and then I have office hours if you guys have questions.